In this video, we are going to talk about the Z transform. What sort of parallels can we draw from the Laplace transform in the Z domain? How it relates with discrete time Fourier transform, and we would look into the region of convergence for the Z transform. Note that Z transform is for discrete time signals and systems, whereas Laplace transform was for the continuous time signals and systems. Now let us start our discussion using systems and say we have an LTI system. So for this LTI system, if we are giving an input which is unit impulse delta of n, so at the output we would be extracting out the impulse response which is h of n. So we say that this impulse response characterizes this LTI system fully. And by that we mean that if we are going to give any arbitrary new input x of n, we would be able to find the output, that is y of n, by means of a convolution, that is h of n convolved with x of n. Now in the Laplace domain, the input that we considered was simply a complex exponential, that is e raised to power st, and we say that s is equal to sigma plus j omega, where this is the real part and j omega is the complex part. So we can break it into e sigma t times e j omega t. Similarly, in the Z transform or in the Z domain, we again consider x of n to be complex exponential. So from the continuous time, we move to discrete time and say we again set ESN. We can break this into again the real part and the complex part. So we would have E sigma times E j omega, and we can extract out the power n outside. Now this is something that we call as OR, and this would be retained itself, and this is a standard definition of the variable z in the domain. So therefore z is equal to or e j omega. Now coming back to this expression, let us say we are giving the complex exponential which is z raised to power n as the input. So this is our input, and we are interested in the output, that is y of n. And from here we know that the output would be equivalent to the convolution of impulse response with the input. So using the convolution sum equation, that is, we have a summation from k equal to minus infinity to infinity h of k x of n minus k. So in the second equality we will plug in the value of x of n, so that is h of k z of n minus k, where again the summation is from minus infinity to infinity. Note that in the second equality, the summation is with respect to k. So we can extract out this variable n from this summation. So we can have z power n, and again a summation k equal to minus infinity to infinity h of k z of minus k. Now this whole thing is a transfer function which is h of z. Hence our output y of n is equal to zn h of z. So this means that for the LTI system considered, if you're giving an input which is z of n, at the output again we're getting the same z of n multiplied by h of z. So the function, that is the eigenfunction, is translated from input to the output, it is unchanged, and then we are having a multiplication h of z. This is something that we can call as eigenvalue for this LTI system, and this is our eigenfunction. So the function remains the same, this value would only multiply or scale the given input. Now from here, that is h of z, we have a functional relationship of discrete time impulse response with its transfer function in z domain. So that is, we have h of z equivalent to a summation. Let me change this variable from k to n. That is, we have n equal to minus infinity to infinity h of n z minus n. That is, for an impulse response, we have a transfer function in the z domain. This was from the system perspective. Now moving to signals perspective, a discrete time signal can have its z transform in terms of x of z, where x of z is simply a summation n minus infinity to infinity x of n z of minus n. So for a discrete time signal, this is our z transform. X of n is a discrete time signal, whereas x of z is a continuous time function. Note that we are starting this summation from minus infinity. Hence, this is something that we call as a bilateral transform, z transform. We would also be looking into a unilateral z transform, whereby the summation would start from 0 and terminate at infinity, and within the summation the arguments would be unchanged. So these are the two z transforms that we will come across, but right now we are just focusing on the bilateral z transform. Now there are several benefits of working in the z domain. For example, we can look into the causality and stability of a given system. We can also design and analyze digital filters, but more importantly, we can take a transform of non-converging signals. We would be discussing about the causality and stability in the upcoming videos, but let us look into what do we mean by the third point. Well, let us say we have an output which is a speaker. We are taking a value from the microphone and then multiplying it with the gain, say alpha, and then feeding it back to our input x of n, and then the loop closes, right? So we have an x of n and this is our y of n. Over here we would have a delayed version of the output, which is y of n minus 1, that would be multiplied by gain alpha, and we have a positive feedback. So we can simply say that our output y of n is equal to alpha y of n minus 1 plus the input x of n. Now let us say that the value of alpha is greater than 1, right? So whatever we are getting a signal at the output, we are multiplying it with a value which is greater than 1 and then feeding it back. So this behavior would indicate that at our output, which is y of n, we would have a signal which would start at certain input and it would increase. So say our input x of n is simply delta of n, which is at time instant 0, it has a value in discrete time which is 1. So this is our output y of n with respect to n. So in one time unit, since alpha was greater than 1, so the value of output y of n would increase, and it would continue to increase as time goes. Now this is a signal which can be represented in terms of an expression, say alpha raised to power n u of n, because starting at time 0 and moving towards right. And then we have a value of alpha which is increasing as we increase the value of time index n, and moreover alpha is greater than 1. Now if we need to take the transform of this signal, say we take the discrete time Fourier transform, which is simply that initially we said our z is r times ej omega. So if we set r equal to 1, so we would converge to discrete time Fourier transform. So that is, we can have a Fourier transform which is y of j omega. This would be a summation n minus infinity to infinity y of n e minus j omega n. But this is a sinusoid, and y of n is a growing function, as we can observe over here in this plot. So hence y of j omega would not converge. Hence discrete time Fourier transform does not exist for this signal. On the other hand, if we take the z transform of this signal, the output, that is y of z, so we would have summation n minus infinity to infinity discrete time y of n z minus n, where this variable z is simply r e j omega. So y of z would be a summation n minus infinity to infinity y of n or minus n e minus j omega n. Now we have a difference between the z transform and the discrete time Fourier transform. And the difference is that over here we are multiplying with another signal which is r raised to power minus n. And we're hoping that this r of n is another signal which is going to pull this signal down, so that if r of n is multiplied with y of n, the cumulative signal is basically converging. That is, we may say that this r of minus n with respect to n at time 0, say this is this signal and it is converging as we move on. So if we multiply this with this, so overall converging behavior. Hence the z transform of this would exist. So from these two expressions, we also have a functional relationship between a discrete time Fourier transform and a z transform. Say we have an input x of n and we multiply that input with the function or minus n, and then we take the Fourier transform, that is discrete time Fourier transform of this function. Eventually we would have a z transform. Or in other words, if you set r equal to 1, so this expression would converge to discrete time Fourier transform. That is, if you set r equal to 1, so this whole thing would become 1 and you will fall back to the discrete time Fourier transform. Now let us look further into this variable which is z in the z domain. So this z is again r e j omega, where this is the magnitude and this is the angle. So let us say we are taking in the real part of z, so this would simply be r cos omega. Now this is a sinusoid and this is a multiplicative factor. So we have a sinusoid function which is being multiplied with r. If r is greater than 1, so in that case we would have a growing exponential, that is, it would expand in time, and if r is equal to 1, it would not change, and for r less than 1 we would be having a decaying exponential or a decaying sinusoid. So all would determine the converging behavior of a given signal. So we will come back to this in a while. But let us now move towards the S-plane and the Z-plane. So in the S-plane, we know that we have sigma with respect to j omega. So we can further divide the y-axis in terms of pi, 2 pi, 3 pi, 4 pi, and so on, and similarly on the negative side. So in the S-plane, which is for the continuous time signals or systems, as we increase the frequency, the oscillations would increase. But for the Z-plane or the Z-domain, which is for discrete time signals or systems, if we increase the frequency, the oscillations would only increase up to a point. And then they would fall back. Let us demonstrate this point with the help of one example. So over here we have a signal which is cos of omega naught n. So in the first plot we are setting omega naught equal to 0. So if we set omega naught equal to 0, we simply have cos of 0 n, so which is simply 1, and we have just one DC value which is equivalent to 1 throughout. But say we increase omega naught to pi by 8, now we would start to have some oscillations. Next, if we increase omega naught to pi by 4, the oscillation would increase. It would continue to increase until we reach omega naught equal to pi, where at every increment value we have one oscillation. So plus 1, minus 1, and so on. And then it would start to decrease. When omega naught is 7 pi by 4, 15 pi by 8, and at cos 2 pi, when omega naught is equal to 2 pi, we would have exactly the same signal. So this is exactly the same signal which is given over here. So the oscillation would increase until a point, and then it would start to decrease, and then the behavior would repeat itself. So this means that for discrete time signals, so whatever is between 0 to 2 pi would be same from 2 pi to 4 pi, or from 0 to minus 2 pi, and so on. So we are only interested in the range from 0 to 2 pi, or from minus pi to pi. So this formulates the intuition for the Z-plane, where again we have a real axis and an imaginary axis, where z is equal to or e j omega. So say we consider a unit circle, so in which we have r equal to 1. In this case, z at r equal to 1 is simply e j omega. And from the Euler's identity, this is simply cos of omega plus j sine of omega. So when omega is equal to 0, so this means that cos of 0 plus j sine of 0, this is simply 1. So from here, when cos is 0, we only have the real part, which is having a magnitude of 1. But when omega is equal to pi by 2, so this would become 0 and this would become 1. So we would get this point. So hence we are moving from the real part to the complex part in the form of a circle. So we are starting from omega naught equal to 0, which is the point over here. Then over here we have pi by 2, this is simply pi, 3 pi by 2, and then 2 pi, which is also equivalent to 0. So you can observe there the translation, that is from this point. Now this is basically made into a circle, thus it formulates our Z-plane. So this would also mean that, say we have a signal x of n, which is cos of omega naught n, and this is simply a sinusoid signal which is having a value of 1 at origin, and then there is oscillations. Now the Fourier transform of this signal, that is the discrete time Fourier transform, this indicates that from 0 to 2 pi, whatever is there, that would also be repeated over here, and then it would be repeated over here as well, and so on. So this cos of omega naught n, we can break it down into exponentials by Euler's identity. So that is, we can have 1 over 2 e j omega naught n plus 1 by 2 e minus j omega naught n. So this means that from these exponentials, we would have two direct delta functions in the magnitude response. So we're going to have one delta function at omega naught, and you can say this is simply delta of omega minus omega naught, but at the same time we would also have a mirror image of it because this is an even function. So we would have delta of omega plus omega naught. So we have two phasors, two exponentials. One is stationed at plus j omega naught, that is e plus j omega naught, and other one is e minus j omega naught. This one is moving in this direction and this is moving in this direction. So this is simply minus omega naught. So since across 0 now we have minus omega naught and plus omega naught. Similarly over here we would have another impulse towards left of it and towards right of it. So this would simply be delta of omega minus 2 pi plus omega naught, and this would be delta of omega minus 2 pi minus omega naught, and similarly it would be appearing over here. Now coming back to this example of our speaker system, where we have said that our y of n is alpha and u of n. So what would be the z transform of this, and what would be the region of convergence? Where does, or for what values of z would it converge? Let us look into that. So hence for that problem we have y of n is equal to alpha and u of n. And since it was a growing function, we know that alpha is greater than 1. So we are asked to find the z transform of this. That is, we would have y of z. So this is equivalent to a summation n minus infinity to infinity y of n z of minus n, where we can plug in the value of y of n in this equality, and we would have alpha n, and u of n would make the lower limit equal to 0. So the limit would start from 0 to infinity, and we would have z of minus n. Or simply we can have the summation alpha by z power n, where n is from 0 to infinity. Now this is a geometric series. It will converge if alpha by z is less than 1. Otherwise it would diverge. So hence in fourth equality we can say that this is equivalent to 1 over 1 minus alpha by z, given that the real value of alpha by z is less than 1. So we are interested in only the real value because the complex value is just oscillating and it is not growing or decaying. So the real value basically pulls down the signal or converges it or it diverges it. So as this dictates our ROC, that is the region of convergence, and we can say that the real part of Z is greater than absolute value of A. And we can simplify this further, and we can say this is simply z over z minus alpha or a. So with respect to the region of convergence, this is our real part and this is the imaginary part, and over here we have our unit circle. So we have a 0 at origin, which is over here, and then we have a pole at alpha, but in the statement we have said that alpha is greater than 1, so hence this was a unit circle, so we have a value of alpha which may be over here. So this is our alpha. So absolute value of alpha. So this means that now again we are making a circle which is at alpha, and the region of convergence is basically outside of this pole. It's not inside. As we were not able to take the discrete time Fourier transform of alpha and u of n for a greater than 1, but at the same time we were able to take the z transform. Now for the same example, say that is y of n is equal to alpha and u of n, but now say alpha is less than 1, but at the same time it is greater than minus 1. So all of these steps would remain the same and we would still get the z transform, which is this. That is, we would have y of z equal to z over z minus a, and again with real part of z greater than absolute value of a or alpha. To understand the absolute value of alpha, say we take alpha equal to plus 0.5, and we can also take alpha equal to minus 0.5, and then we can solve for both. Now in terms of the z-plane, this is our unit circle. So in this z domain we have a 0 at origin, but right now we have a pole at 0.5, and we can draw a circle across it, and we can say the ROC is outwards of that circle. On the other hand, again we have a unit circle with 0 at 0, but right now the pole is at minus 0.5. So we would draw again the circle across 0.5, and we would say that the ROC is towards outside of that circle. Now for these two different values of alpha, we have a very similar looking z-plane, but we can elaborate the difference with the help of a frequency response. So we mentioned that z is equal to odd e j omega, and the translation from z to the discrete time Fourier transform is by means of this or. Then we set or equal to 1, so we would simply have e j omega. Hence we can have y of e j omega as the frequency response, from where we can find the magnitude and the phase. So this is simply e j omega over e j omega minus alpha was plus 0.5, so now we would have 0.5, and similarly for alpha equal to minus 0.5, the transform is e j omega over e j omega plus 0.5. So in terms of the magnitude response, that is, we are interested in the magnitude y of e j omega for both the cases. So this is 0, and we mentioned that from minus pi to pi is all that we need, and after that the response would be repeating itself. So when omega is equal to 0, so this would mean that y of e j omega, when omega is equal to 0, so this would simply be 1 over 1 minus 0.5, so hence it would be equal to 2. At 0 the value is 2. So next, let us take the terminal value when omega is equal to pi. So when omega is equal to pi, so this would simply be minus 1, and we would have minus 1 minus 0.5. This would be equivalent to 1 over 1.5, and that is 0.75. So at this point we simply have 0.75, which is over here. And similarly the same would be for minus pi, and hence we would have 0.75. So as the magnitude response would simply be like this, and after pi we would have the same thing repeated over here and here. But for alpha equal to minus 0.5, that is, we are having this transform. So when omega is equal to 0, we would have 1 over 1.5, that is, we would have a value of 0.75, and when omega is equal to pi, this function would have a value of 2 at this point. So we would have this magnitude response. And similarly, we would have some differences in the phase plot as well. Now, previously we have discussed y of n by means of alpha and u of n. That is, it was a right-sided signal. What if the signal y of n is left-sided? That is, we have minus alpha and u of minus n minus 1. This means that for 0 and onwards, the values are 0, but for minus 1, minus 2, minus 3 and onwards, the values are actually decreasing. So we are interested in finding the z transform of this function. So y of z is the summation n minus infinity to infinity, the signal y of n, that is, we have minus alpha n u of minus n minus 1, and then z minus n. So we can bring out this minus, which will come here. Next we have a unit step function with an argument of u of minus n minus 1. Note that this u of minus n minus 1, so this would be equal to 0 when minus n minus 1, that is, this argument, whole argument is negative, is less than 0. And this would be equal to 1 when this whole argument is positive. So we can rewrite this as simply n is less than or equal to minus 1. Hence u of minus n minus 1 would be subsumed in this summation, and we would have a summation that would start from minus infinity, but now it is limited to minus 1. And we have alpha and z minus n. Now we can apply a change of variable. That is, we can introduce a new variable which is n tilde, and this is simply equal to minus n. So hence our summation would have n plus infinity because of this change in variable to 1, and minus n tilde z of plus n tilde. Now again, just for simplicity, let me again call n equal to n tilde. So this would simply be z by alpha power n. Moreover, if we are starting a summation from infinity to 1, this is equivalent to starting a summation from 1 to infinity. That is, you start summation from here until this point, or you start summation from here until this point, it remains the same. So as we have this formulation, which is very near to geometric series, but still it is not there, because our geometric series is usually in the form n equal to 0 to infinity, z by alpha power n. But right now we have a summation which is starting at 1 and going to infinity, and we have z by alpha raised to power n. We have a value of this summation when n is equal to 0, which is missing. That is when n is equal to 0 is missing. So if we plug in the value of n equal to 0 in this function, so anything raised to power 0 is simply 1. So we would have 1. So we can bring this function towards the left side and this function towards the right side. So hence from this equality we would have 1 minus n is equal to 0 to infinity z by alpha raised to power n. Now this was our y of z. As this is equivalent to 1 minus 1 over 1 minus z by a, given that this is less than 1, that is the real part of z by alpha is less than 1, or real part of z is less than absolute value of alpha. This is our ROC. But we can simplify the algebraic expression further. So we would have, let's simplify this first. So we would have alpha over alpha minus z 1 minus, and then taking the LCM we have alpha minus z, alpha minus z minus alpha. So this would cancel off and we can have an expression which is z over z minus alpha, y of z. Now this expression y of z for minus alpha raised to power n u of minus n minus 1, this was having z over z minus alpha. So this is exactly equal to our prior discussion and prior example where we had alpha of n u of n, which was having the z transform as z over z minus alpha. So the algebraic expressions are the same, but ROCs are different for both of them. So presently the region of convergence is that. Now again we have a unit circle, but the pole is at alpha. So say this is our alpha. So the ROC is inward. Previously it was out of it, now it is inward. So this is when alpha is actually less than 1 but greater than minus 1. In the next discussion we would be talking about some of the properties of the region of convergence.